The title of this paper is Video Codec Performance Validation and Emulation and Post-Silicon Using Portable System Standard, Stimulus Standard. Authors are Suresh, Vasu, Nithin, Venkatesh, Joydeep, Maitra, and Vinit, Shenoy from Intel. Again, as a reminder, we have allotted 20 minutes for video presentation by the authors, followed by 5 minutes of Q&A. Please use the Q&A tab on your screen to post questions as we go through the presentation, and I will pull up the questions at the end to post to the authors. Also, there's a poll option which comes with the Q&A tab. Please provide your input ratings at the end of the paper presentation for best paper selection. Okay. With that, thanks, and let's move on to the next presentation. Over to the Intel team. Please go ahead.
Good morning, all. Myself, Nithin Venkatesh. I am from Intel India Pvt Ltd. My co-authors are Suresh, Vasu, Joydeep, Maitra, and Vinit, Shenoy. So before we start our presentation today, I would like to share why and when did we thought about this approach or methodology, which I'm going to talk about this throughout the session. So what was the need of this? What made us to think, okay, fine, let's bring in PSS into our flow. When we were working in media validation, the amount of effort which we were putting to generate the test content itself, to develop these test content, media validation test content, it was humongous manual effort was involved, and the time taken to complete this test generation task itself was time consuming. It was all due to a lot of manual effort was involved because a lot of SOC level configurations, combinations was there. We have to meet all the requirement. So we as a team, we work on more on performance validation, which includes a lot of stress scenarios, end-to-end use cases, wherein architects use it to come with a lot of new requirement to meet that performance. At that crunch point where data which we have to deliver has to be on time with precision, because the performance data has to be precise. With a lot of manual effort which was involved to generate the test content, this is just one of the reasons to generate the test content. It was very difficult to meet that requirements which was coming from the architects. So that's where we thought about why not PSS? Why not bringing PSS into our flow during a test content, where we can do a lot of automation, we can do a lot of improvisation. So today, I'm going to talk about our paper, which is Video Codec Performance Validation in Emulation and Post-Silicon Using Portable Stimulus Standard. So let's get started. Today, the challenges faced during post-silicon validation is huge because due to a lot of high levels of integrations, more IPs are getting integrated, which automatically increases the SOC complexity. And as you work on a complex architecture, the challenges will also increase. There will always be a continuous ask of platform performance requirements, which will be competitive. So we as a post-silicon validation engineer, we must work on test content preparedness before silicon arrives. So we work on emulation platform before silicon to develop the test content and to validate the corresponding scenarios. So test content generation will be done keeping all the system level SOC configurations, combinations, so that once we have the silicon, we are ready with the test content to validate. So as I mentioned earlier, in our media validation, a lot of manual effort has been put during the test content generation. Given the multitude of the SOC configurations, the interconnect topologies, n number of masters and slaves, which will get involved during an use case scenario at SOC level, stress testing, the list goes on. So during silicon bring up, when we are debugging one of the performance issue, this was just during one of the performance issues which we have seen during silicon bring up. And we end up tweaking our own test content to meet the requirements, which again involved a lot of manual effort, which was time consuming for us. So at that point in time, we were just thinking about what was lacking the most in our flow, or the existing flow, which I rather say. So the most lacking part was flexibility in the test content generation. With all SOC configurations getting involved, So with our defined methodology, using PSS, we were able to achieve the flexibility to generate the test content so that our focus would shift to validate and provide the results much faster rather than spending time in generating the test content, validating those test content manually, whether we have achieved all the or met all the requirements which was architect has assigned, asked us with all the different combinations by bringing up one particular IP, disabling one particular IP. So all this tedious task was achieved using our methodology. Okay. So after discussing our problem statement now, so this is just an overview which I wanted to share about PSS, which is portable similar standard. So this is a standard PSS flow which we use in our emulation platform and post-silicon validation. So first of all, here we do the modeling of all the components with all the necessary PSS slips which gets involved. So next we do the scenario generation part, and this is where I was talking about multiple sock configurations getting involved with a lot of constraint we inject here, which will be defined here, and then pass to just content generation flow. So with all the constraints being defined and then injected into the PSS flow, the test gets generated with all different sock configurations. So once we have the test, we will execute and validate the test in emulator. So once the test executes, we debug or analyze using log files, calculate the performance values based on inbuilt interconnected performance counters, and we do the latency measurements. So also we do coverage analysis on what functionality is being covered. So in this debugger analysis using log files, what we do is more on because we were working more on a performance validation. So there were a lot of inbuilt performance counters were there, so that was getting printed. We has to initiate or inject or develop some small automation steps to kind of validate those log files, and then we reuse the same test content generated here during silicon bring up also. So that was our main intent, because when we work on test generation part, so that has to be reused in our silicon bring up. So whenever we face any issues in during silicon bring up, we just move back to the original test content flow, generate it, and then bring it back here and then reuse it to validate our media functionality and performance. Okay. So moving on now, before we discuss how the PSS has helped us, I just wanted to give the overview about what exactly we do in our media. So this is just a typical video coding flow. So in our media terminology, we will encode the incoming video or image, reduce the bandwidth for the transfer. With a minimum transfer rate, we are able to transfer the encoded video or image. And then we generate the test content without any quality loss, which will be used for our use cases. So this is just a general flow for us. So here when we have the video or images, which will be passed as an input, as of current trend, there are multiple encoding techniques are available. So one of them is just mentioned here is spatial model, wherein all the redundant data within a single frame will be removed and passed to the next level. Similarly, there's another encoding technique, which is temporal model, also does a similar functionality, but with multiple frames. So once we transform the data, later it will be quantized at different level, which will have an impact on the quality of the image or video. So with the quantization, different levels of quantization, we can actually play around with the media, image or video quality. It directly affects the media, image or video, and then reordering followed by entropy encoding, which is more about reduced bandwidth. So in this entire process, it involves multiple parameters. For example, size, resolution, different formats, which is RGB, YUV, and frequency with which our DMA should transfer. With all different parameters which we enable or disable during the test content generation, which determines the performance of our media. So even we end up in tweaking around a lot of IP level configurations, which are defined parameters. So due to the requirement which has come up, so we have to go and tweak around with those options, and then just to see the performance validations with and without a specific IP block. Okay. So now coming back with a typical SOC with the codec and a lots of other multimedia. So here we can see multiple instances being defined. So in our performance validation, we will have to define stress scenarios, as I mentioned, with the different resolutions, like for example, 4K, 8K, with multiple frames. So we have concurrent scenarios also, where multiple instances of codec work in parallel. As explained in our previous slides, major requirements are with SOC variants, with different clock speed, NOC configurations, and multiple FSP of DDR. So then we have end-to-end use case scenarios where codec working with other multimedia masters like graphics, display. Like codec will do the decoding and have to display it. Similar way, graphics will render the image, and that rendered image, our codec should encode it. So like this, we will end up with lots of software use case scenarios, which involves our codec with a lot of multimedia blocks, which is present in our SOC. So which we will end up in doing a multiple SOC level use cases. So that is where we work on developing the SOC level use case scenario, use case generation part. Okay. So now coming back to the PSS now. So the main discussing point is why PSS for our media validation, what and how PSS is being used. So we came up with this methodology which uses PSS to constrain all our required parameters and generate the desired test content. So our C model generates the test content with all the randomized parameters and also generates the corresponding output reference data, which we'll use to validate our test content in our post-processing stage. So this was our methodology using PSS, which will not only help us in reducing manual effort, it also helped us in planning use case scenarios, pipeline scenarios with ease. So one of the major requirements which we had while doing our media validation was for PSS was a DMA address overlapping. When we do encode or decode separately, when I say separately, when we do it individually, with having only one instance is being involved there, the C model used to generate a generic DMA address location. So running individual test content, individual functionality of a media would not be a major problem for us, because it'll have its own media DMA address location space where it will go and do the transfer, where we'll go and go inject or preload the backdoor load the content before we do a processing. But when we do encoding and decoding parallelly, when I say parallelly, we have two multiple instances trying to do a media transfer. When I say media transfer, it's encoding or decoding together. We end up in DMA address overlapping issue. So we had ended up with that issue. So then PSS helped us in taking care of this issue by generating a test content in such a way that the DMA address overlapping was taken care. Like example, let's consider JPEG decoding has started, so the JPEG image must be preloaded in a DMA address, in a specific DMA address. And at the same time, video encoding parallelly, we should also be accessing a different DMA address location. So all this preloading part, and then at the end, we'll have our output reference data, which is getting put in the DMA address location. So all of this were taken care in such a way that the entire range for one specific transaction from the go start till the end has been taken care separately into considerations. So giving those constraints when it generates the test content, it is taken care. So the DMA address location was one of our major concern when we were trying to do a lot of manual effort. We have to calculate the entire address location space where an decoding will take, and then we have to go and make sure that those address locations were not getting overlapped. So this was one of the example which I wanted to share because that has eased our flow and execution wise. So then with these address overlapping issue, which definitely got resolved for us. So the test case generation was seamless for us. and it was more ease for specifically for scenarios such as pipeline scenarios, concurrent scenarios, and use case scenarios. So for those sort of software scenarios, it was pretty much easy for us. So these are the few snippets of the components used in PSS. So let's consider we have component decoder and component encoder. So in each components, if you see, we have action media backdoor load and action media encoder or decoder. So in action media backdoor load, the one which I was just explaining in my previous slide, more about the backdoor loading of the media content, image or video. So we do this in this action, the image or video backdoor loading before we encode or decode. So in the media action, we set all the desired configurations which will be constrained. So here, when I always mention the desired configurations, it again comes up with all the SOC combinations, different clock frequencies, which was desired for that particular transaction, and then which master, which slave, which I'm going to explain in the coming slides, how exactly, we just give some examples. So all of this will be constrained and processed. So even we have something called post-solve. You can just see in this media action, we have all these different combinations of constraining of all the desired configurations. And then post-solve, which deals with the post-processing, checks after decoding and encoding. Like when a decoding and encoding is completed, it generates an interrupt saying that my encoding is done or my decoding is done. So then it dumps out all the output reference data. So we have a golden reference data, and then we have to compare a bit by bit. So wherein whether the output generated data, it matches the desired golden data or not. So all of this is also taken care with the scripts, which just runs it in the test content, it just generates it and it gives us the data. Similar way for decoder, which I was just explaining till now, is on for the encoder part. So similar way for decoder, everything is fine here, everything is same. And then the only difference which you use here is the data set. Whatever we just did in encoding part, all of this encoded image or encoded video, we'll take this as a data set and then give it to decoder. So the rest flow remains the same. And then here, one more thing is you can see the decoder action media and then encoder action media. Both are actually being same. Most of them configurations wise and writing those actions. It's most of them are actually can be reusable. Okay. So now this is just one of the generic PSS code which I wanted to display here. So this is a very minute level of constraint which we have used. So if you can see here, the constraint which I'm talking over here is constraint in core. Which core initiates the transaction? So we have multiple core in our SOC. So which core comes and generate the decoder, enables the decoder functionality. So we have to control that as well. So that everything for the concurrency scenario and then pipeline scenarios, we wanted a multiple core getting involved here. So that is what we just you can see here. That is what we have constraint here, and similar way we have constraint size. Like it starts from 4K, 8K, 1080p, and 300 × 300. Everything can be constrained here. So the size of the particular image, everything can be constrained. So which media type, basically whether it's encode or decode. So all of this have been taken care seamlessly, and this is just one of the examples which I mentioned. Similar way we have done these lot of configurations here. So going on now, so when we do a performance validation, we don't concentrate on or target only on single master transfer. So as I was explaining, we do have multiple master scenarios where we must validate performance. So as you can see here, we have two cores where here trying to perform a JPEG decoder and a video decoder. Assuming core 0 tries to decode the image of resolution 300 × 300 and core 1 tries to decode the video. So in this concurrent scenario, both will try to stress the system while transferring the data. It might be stressing NOG, the interconnect. It might be stressing the DMA, which holds off all the data, transfer coming in, transfer going out with all the output reference data, it's getting put into DMA. So we do performance calculations based on these scenarios and with master and multiple masters. For this, Concurrent scenarios, as I mentioned, that we do generate the test generation part using PSS. So we have one advantage over here using PSS, that we use it to see the graphical representation of this concurrent scenario, which we generated by PSS. It has all the information required to generate the test content without any overlap, as I mentioned. So like if we can see, the instances of decoder are taken care in the graphical representation. Even the core assignments are taken care with clear information about whether to decode or encode. This gives us a leverage to actually target more concurrent scenarios with so much ease while generating the test content. So this helps us. This graphical representation itself is which only will helps us saying that, okay, fine, now we have all of it has been defined here. So this is how the flow will go. So this is how the test case will get generated. So moving on now, this is called a pipeline media test cases. So as we explained, discussed in our previous slide, the concurrent scenarios. We do have these pipeline scenarios where one master completes the process and then only the next starts. So everything is in pipeline. So even that is also taken care in phases while generating the test content. If you see in this also, core assignment, DMA buffering is taken care. So there will be no overlapping. So even here also, the entire core perspective, execution perspective, with respect to the test content generation requirement, however we want, we can generate using the PSS. So in overall, our methodology has helped us develop the test content using PSS by 80%. When I say this 80%, it's more about test content generation part, compilation of it. It's all included part of it. It has literally helped us using PSS by 80% of it. Even with this methodology, we were able to generate the test content for concurrent and stress scenarios with ease, even though it involves multiple soft configurations. The development time has become more effective due to PSS. With this, even the coverage data fetch was also easy with the PSS getting involved. So if you can see here, the amount of data which we have used, or the amount of data which we have seen here, is saved here basically. The amount of time which we have saved here, like all this orange, you can see it's orange, and from the PSS column you can see this 25 to 25, 20 to 25 days is max is what we have taken. But when we did in the manual, this is just a direct comparison between our previous project and the next project where we use this methodology. So this is how the result turned up. The amount of time which took, like for the decoder IP level test cases, around 75 days and 90 days. So this is the number of days which we took, and then the amount of number of days which got reduced using our methodology was a huge benefit for us, and then it saved a lot of time for us. Coming to the results part, it's reusable seamlessly. Here we are able to reuse the test content which was used in emulation during silicon bring up, and we used to correlate the performance data. Reduce a lot of manual effort. This was the most effective and flexible methodology which helped us to reduce our manual efforts in test content generations, saves test preparation time, easy to collect coverage, helped us to generate stress or concurrent scenarios, even use cases or end-to-end scenarios. In total, our media execution has become so smooth, all due to our methodology. Thank you all.
Okay, thanks, Suresh and team. That was a very good presentation. We're just about time, maybe a couple of questions. So one question is, I think you showed an IPC reference model in your presentation. So is that a functional accurate model, or is that cycle accurate, and it's used for performance performance assessment as well?
Yeah, Shish. So actually, that's a C model we received from the IP team. So for it's an cycle accurate, and they have used for their performance, but it helped us to generate our test content also. So we save the time of writing the constraints and everything. So we collected the model, got the constraints from them. So then we used the perspec on top of that.
Okay, understood. Thanks. Another, maybe one more question is, so you've described the flow that helps you to generate tests for different scenarios in a very efficient way. Now, for these different scenarios that you generate the tests, how are the performance targets defined? And are you also, does this framework also help you to do any bottleneck analysis to, figure out where, which parts of the design are actually acting as a bottleneck?
Yes. So from the performance side, from the performance architecture side, we already had the expectations. So from their model calculation, everything, we got the expectation. So we created the direct scenario using the perspective. We didn't randomize everything, but we use the perspective to directly match those scenarios. And then we are able to measure the performance, because all the performance counters, everything was incorporated in the perspective generation itself. So we were able to calculate that, and we are able to there were some scenarios where it was not matching the expected performance when we were testing in the emulation. So then we debugged it, and we have root cause that some of the configuration issues. We didn't find any silicon or design issues, but we are able to rule out all the configuration issues before silicon came. But when the silicon came, we are almost from the day to third day onwards, we are able to run the content immediately.
That's great.
So that was the biggest advantage.
Sure. Any further recommendations on improvement to make this flow more robust from you guys' side? Anything on your next to-do list?
No, only we felt was the modeling expertise, right? That was not there with us. So we are more dependent on the external resources to do that modeling side. So that is where the one dedicated resource was allocated for that. So that expertise, maybe it has to be built for the long term to move on to deploy the perspective in multiple different IPs. That's the one thing we really felt.
Okay, excellent. Thanks for that presentation. Really good work, guys. Thanks.